So, welcome back. So, we were discussing about the powder metallurgy module, and we have already discussed about the different powder particle shapes and also how to determine and how to define their characteristic dimensions. So, we will go ahead with the powder preparation and several powder metallurgy processes. So, first in the process is mixing or blending, like we have discussed earlier also. So, where we combine metallic and non-metallic powder with additives to get the desired mixture. So, most powders are mixed with other powders, binders and lubricants to achieve the desired characteristics in the finished product. So, this is a typical example of a mixer or agitator. So, there can be several kind of mixer that we generally can be used for powder metallurgy. For example, sigma blade mixer, also we can use. So, that is one variant. Another variant can be jet blade mixer, and also there can be like extruders. We can also use extruders for getting the mixture, the powder additive mixture. So, that we can achieve, and with that mixture we can go on for the subsequent processing steps. So, sufficient diffusion must occur during sintering to ensure a uniform chemistry and structure, so that we can achieve the desired microstructure and properties in the sintered parts. Unique composites can be produced by powder metallurgy route, which is otherwise difficult, even not possible to manufacture by other routes, like for example melting casting. So, blending or mixing operations can be done either in wet or dry condition. So, like the case of ball milling, where we mix a number of metal or non-metallic powders together. So, there we basically the goal is to achieve the powder mixture itself, which can be done in dry condition. Even however, we generally do the mixing of the powder with the aggregate, the additive, to develop the powder aggregate or the green mixture. So, powder additive or binder mixture, that is mostly done carried out in wet state, where the additive gets phase transformation happens from solid to liquid, and that also facilitates as a binder to mix the solid powders. Okay. So, the mixed powders are then compacted in a die to form the size and shape of the desired part. Parts for produced are known as green compact. So, that is the first step of powder metallurgical processes. That means achieving the green compact shape from the powder aggregate, and then the density after compaction is called green density, which depends upon the compaction pressure, dimensions of the compacted parts and powder hardness. So, the compacting is carried out at room temperature in dies. The die cavity is filled with required amount of mixed powder for uniform distribution of pressure. So, it depending upon the part geometry that is going to be produced. The part can be produced using 2 punch system, also by single punch system, or even a multiple punch system. So, so that is that can be determined or decided on case to case basis. So, compaction is performed using dies machine to close tolerances, because so once we get the green compact ready, so we can achieve a desired shrinkage as per the presence of the polymer or the additive component in the powder aggregate. So, which is need to be removed subsequently, and then the compact need to be densified by thermally activated process, that is sintering. So, to achieve the desired part geometry. So, generally the dies used for powder metallurgical processes are made of cemented carbide or tool or die steel pressed using hydraulic or mechanical presses. So, where the pressurization is achieved by hydraulic or mechanical means. So, the basic purpose of compaction is to obtain a green compact with sufficient strength to withstand further handling operations, and the green compact is then taken for sintering, for that, which is the last step. And then, so the compaction, so applications, so porous metals and filters. So, in that case the pressure range is around 40 to 70 MPa. Refractory metals and carbides, the pressure ranges between 70 to 200 MPa. for porous bearings, machine parts. So, for different application this is the pressure ranges. When there is uniaxial compaction is concerned, it is given over here. So, why there is a lesser pressure requirement in case of porous metals or filters, because end goal is not to achieve a dense part, rather end goal is to achieve a porous parts where there is porosity at the so you can say so these are basically the porosity that is present in between the powder particles, which also serves as the intended purpose of lubrication in case of porous bearing. And also another example that I have given you, that is the purpose of capillary wick, where this wicking structure is basically used for capillary pumping. So, the porous objects are having several different applications based on their individual need. So, the green compact is taken for sintering. So, hot extrusion, hot pressing, hot isostatic pressing are some of the examples where we generally do the compaction at high temperatures, but otherwise in all other uniaction compaction processes it is done at room temperature. So, so hot pressing, hot extrusion, hot isostatic pressing, these are the examples where we do the densification and the pressurization together, and to achieve the improved set of properties in the and also higher density than we can achieve in case of uniaxial compaction techniques. So, this is a typical example of a compaction machine. So, where we can achieve, we can utilize for uniaxial compaction. Okay. So, the compaction sequence. So, the powders do not flow like liquid because they simply compress until an equal and opposing force is created. So, this opposing force is created from a combination of resistance by the bottom punch and friction between the particles and the die surface. Okay. So, you can see this is the start of the cycle. So, this is the punch, this is the die, and this is the bottom punch. So, in this case you can see that bottom punch is stationary up to a certain, up to the compaction is getting completed, and only the top punch, that is basically after placing the feed powder aggregate within the within the die, then the upper punch moves and it compresses to achieve the desired shape of the powder compact, and then the upper punch goes out, and then the lower punch moves for the first time to eject out the compact once it is made. And then this feed shoe basically is responsible for lateral movement. So, then it is basically facilitates removal or ejection of the component out of the die punch system, and then the next charge of the powder aggregate is incorporated into the die cavity by the same feed shoe. Okay. So, this is basically the steps involved in compaction. So, additional considerations during compacting. So, when the pressure is applied by only one punch, the maximum density occurs right below the punch surface and decreases away from punch. So, this is a typical case. Assume that we are dealing with a cylindrical specimen. So, what happens if we are dealing with only one punch? So, then there will be a density gradient, that means there will be higher density up to a certain depth from the top, where we are only talking about a top punch system, and then the density will be lesser towards the bottom of the cylinder. And when we are talking about a 2 punch system, if the same cylindrical powder aggregate, we are dealing now with a 2 punch system. So, then what will happen? So, there again there will be a density gradient, and in that case there will be a density gradient from the bottom, from the top as well, and in the corner areas there will be a lower density region. So, what will be the implications of this? The implications will be so during sintering, as these are the areas where the density is lesser than the other areas. So, then there will be the differential densification rate that will be achieved in case of during sintering, and which will cause higher shrinkage in these corner regions because of the lesser green density achievable. So, then the end result, so the after sintering, this part will show a dumbbell shaped attributes because of the differential shrinkage at different locations along the powder aggregate. So, what are the remedies to overcome this defect or this difficulty? We will learn about that later. So, the density distribution obtained in case of a double acting press and 2 moving punches is of course better than the density distribution achieved in case of a single acting press. So, thicker parts can be effectively compacted in this way. So, the effects of compacting. So, the average density of the compact depends on the amount of pressure that is applied, with the specific response being strongly dependent on the characteristics of the powder being compressed, that is its size, shape and surface texture, mechanical properties, etc. Okay. So, the final density may be reported as either an absolute density in units such as grams per cubic centimeter or as a percentage of the pore free or theoretical density. So, the difference between this percentage and 100% corresponds to the the amount of void space remaining within the compact. So, so this is the curve which shows the variation of pressure and green density. So, you can see that as the pressure increases, we are achieving higher green density. So, this is true for regardless of the material, the same kind of behavior we can observe for all different classes of materials. So, so this is the figure which shows that a single displacement will produce different degrees of compaction in different thicknesses of powder. So, it is impossible therefore, for a single punch to produce uniform density in a multi thickness part. So, this is a point that is very important for you to understand. So, that is why I told that the requirement of the number of punches, it depends on the different geometries, different thicknesses, cross sectional thicknesses present in the part which is being manufactured by the powder metallurgical route. So, when more than one thickness is required, more complicated presses or compaction techniques must be employed. Okay. So, so this is a typical example when we are talking about more punches than the top and bottom one. So, you can see this is a typical example where we are using double lower punch while only one upper punch is involved, because of a different cross sectional area at this region to the another region. Okay. So, so you can see that by providing different amounts of motion to the various punches and synchronizing these movements to provide simultaneous compaction, a uniform density part can be produced. So, so if it can also be done by a 2 punch system, that means one upper and one lower. In that case, the movement of punch 1 and punch 2 needs to be coordinated, their motion need to be coordinated in such a manner that they impart a similar level of densification strain to all the parts. That means, if I term this part as part A of the resultant component, this is part B. So, then it needs to be compensated in such a way, because if you can understand that because of the lesser density, lesser cross sectional area over here. So, if there the coordinated motion is not given, so then for the same pressure exerted, we can achieve higher density, higher green density, say if I term it as D green. So, then you can see higher green density here, and we can see a lesser green density in the B section of the component. So, how we can achieve that? How we can achieve a similar density at both these A and B sections of the same part? That is by providing appropriate motion to this lower punch, that is punch 2, which should be compressing this part B at a even higher level than what is being done in case of section A of the same part. So, that resultant density becomes uniform, and the same density uniformity can be retained even after sintering. And what will be the alternative route? Can be by using two different lower punches, where both the lower punches are responsible for exerting a different amount of pressure, so that the resultant density distribution becomes uniform in the part. So, this is the compaction pressure versus porosity contact area. So, increased compaction pressure provides better packing of particles and leads to decrease the porosity and localized deformation, allowing new contacts to be formed between particles. So, because here one thing you need to understand that so like we are doing this compaction. So, how we are basically achieving the green shape of the part? I mean why the powder particles are not I mean just getting dismantling from each other, because during compaction we basically allow the powder particles to form cold welding at the contact points, and this is the I mean process which is responsible for allowing the powder aggregate to retain their shape post compaction, and then those points of cold welded regions are serving as the I mean locations where from the sintering densification starts. I mean the diffusional mass transfer starts during the thermally activated sintering process, and also these are the locations where from the neck formation starts between the neighboring powder particles, and thereby basically we achieve the uniform densification throughout the part, and we achieve uniform density in the sintered part, which is also a primary requisite requirement for utilizing the parts for desired functional or mechanical applications. So, I mean so then so these are the basically powder compaction and slip casting techniques. So, I mean so the powder compaction overview is already given to you, which converts loose powders into required shapes with sufficient strength to withstand I mean subsequent sintering, and classification can be done as pressureless compaction and also as pressure based compaction. So, pressureless compaction example are loose powder sintering. I mean so the advantages of loose powder sintering is low cost equipment and high porosity, like I mean when like we are talking about cylindrical porous bearings, then we can go for tap powder sintering or loose powder sintering, where there is not much pressure is needed, because our end goal is not to get a dense part, rather our end goal is to get a porous object. So, that is why we do not try to achieve I mean as high grain density as we can achieve if we go for pressure based compaction techniques. However, pressure based compaction techniques are very much essential in case the part is going to be subjected to I mean going to be utilized for I mean mechanical application, where I mean structural application, where it should serve as a load bearing member of a load bearing part, or as a I mean sub part of a assembly. So, the disadvantages are difficulty in part removal post sintering in case of loose powder sintering, and also significant shrinkage during sintering. So, I mean so then compensating for the sintering is I mean shrinkage achieved during sintering stage is important in case of loose powder sintering, because I mean otherwise it can cause significant distortion, and then the resultant part may not qualify for that for its intended application. So, I mean so that needs to be accommodated in the I mean desired part geometry, that enhanced shrinkage happens due to loose powder sintering. So, the applications, as I told you, that porous filters, electrodes for alkaline batteries and fuel cells. Okay. So, and then there is another example of a common powder metallurgy technique is slip casting, where a suspension or slip of fine powders less than 5 micrometer in a liquid I mean suspended in a liquid is poured in a mold, dried and then sintered. So, the key slip components are dispersion agents like which stabilizes powders against aggregation. I mean they are enabling I mean almost like a coating over the individual powder particles, so that they does not get agglomerated, so that we can achieve uniform dispersion of powder particles in the green compact, and also that can save anisotropic properties to be generated in the sintered part. And then so other than dispersing agent, there is solvent, so which controls the viscosity and facilitates casting. I mean casting means you can understand that it should be a I mean it is dealing with a flow of the liquid melt, in this case a slurry, where the I mean powder particles are I mean suspended within a I mean dispersion agent and the solvent, and then it also includes a binder which provides strength to green compact. I mean upon solidification or drying out the I mean dispersion I mean agent. So, the and then the plasticizer which adjust binder properties. So, these are the key ingredients needed for a slip preparation to do the slip casting. So, important considerations are proper control of particle size, distribution and additives, that is deflucolants like alginates, achieving low viscosity and low shrinkage while maintaining high strength. Applications of slip casting are large and complex shapes for limited production runs, especially for ceramics and metals like molybdenum, and critical analysis if we do. So, the loose powder sintering strengths are cost effective for high porosity components, simple equipment and processes. Weakness, of course, that is unsuitable for high precision or dense parts, and significant dimensional instability due to shrinkage. Whereas, in case of slip casting, the strength are effective for complex geometries. It is a much cheaper technique and provides better green strength and control shrinkage with proper additive utilization of proper additive. And the weaknesses are, it is a time intensive process due to drying and sintering stages are involved in this case. So, the requires careful preparation of slip to avoid aggregation and achieve desirable viscosity of the powder solvent mixture. So, the critical assessment, pressureless methods like loose powder sintering are ideal for simple porous parts with low structural demands, but have limited applicability for precision manufacturing, whereas slip casting offers versatility for complex shapes and materials, but is labor intensive and requires precise control of slip properties to ensure quality. So, coarser spherical stainless steel powder, a mixture of 80 to 81% metal powder, 19% water, 0.3% sodium alginate as deflucolant having a pH value of 10 can be used. So, what are the steps in slip casting? Of course, preparing a assembled powder plaster mold and then filling the mold with the slip that is prepared with the powder and the solvent and the dispersion agent, and of course, by mixing with the additives, and then after filling the mold, it is the absorption of water from the slip into the porous mold, and because so the porosity present in the mold facilitates as a sink for the water that is present in the solvent, in the slip that is used for developing that particular mostly ceramic parts, and then removal of the part from the mold after the water gets absorbed, then trimming of finished part from the mold. Sometimes mold releasing agents like oil, graphite can also be used, and then hollow and multiple parts can be produced in case of slip casting route. So, the advantages are products that cannot be produced by pressing operation, that means parts having complicated geometry and also parts having hollow cavities of different irregular shaped ones. So, that can be achieved by slip casting, and no expensive equipment is required, works best with finest powder particles. The disadvantage, as told before, that it is a slow process and also labor intensive. So, the applications can be tubes, boats, crucibles, which are generally used for other sintering techniques as a carrier for the samples, and also it is used for turbine blades, rocket guidance fins. So, also products with excellent surface finish like basins, water closets that we generally use for our daily life are being manufactured by slip casting route. Okay. So, similar like slip casting, the another variant is slurry casting. So, this process is like slip casting, except that a slurry of metal powders with suitable liquids, various additives and binders is poured into a mold and then dried. So, the solvent is removed either by absorption into the POP or by evaporation. So, very high porous heat for use as electrodes in fuel cells and nickel cadmium rechargeable batteries are produced by this method. So, the major difference between the slip casting and slurry casting, you can say that in case of slip casting we deal with ceramic powders, and in case of slurry casting we deal with metallic powders. Otherwise, the process is pretty same. And then the another variant is tape casting, which is also called doctor blade casting, which is useful for achieving thin parts. So, this is a variation of slurry casting process and is used to produce thin flat sheets. So, this process involves preparing a dispersion of metal or ceramic powder in a suitable solvent, and then the addition of dispersion agent to improve the dispersion of the particles. Then the binder is added and fed to a reservoir. Whole mixture is fed on a moving carrier film from the bottom of the reservoir. So, I mean, so a typical doctor's blade casting you can understand from here. So, you can see here the parts of having dimensions in the range of 50 to 1000 micrometer thickness. So, you can understand that 50 micron to 1 mm. So, such a low thickness sheets can be manufactured by doctor's blade casting or tape casting route with uniform thickness by that can be achieved by pouring or the slurry over a moving conveyor belt like structure. So, it can be a endless stainless steel belt that is presently used as a carrier tape. So that is how, and then there must be a shearing action of a blade which controls the porosity of that controls the thickness of the deposited slurry layer, and it facilitates avoidance of getting the chances of thickening of the slurry layer locally, which can become detrimental post sintering of the this deposited slurry layer. So that is the role of this doctor's blade, which is kept to control the thickness of the slurry layer. So, you can see it over here. So, and then there is vibratory compaction. So, this process a variation of slurry casting produces thin flat sheets again in the range of 50 to 1000 micrometer thickness. So, a dispersion of metal or ceramic powder, solvent, dispersion agent and binder is prepared and fed into a reservoir, similar like doctor's blade casting. So, it is quite same. So, then the compaction of metal powder. So, brittle powders can be compacted by this method as they develop crack if done by pressure compaction. So, this method is generally used when powders have irregular shape. Use of plasticizers for forming is not desirable, and sintered density is required to be very close to theoretical density. So, important variables in vibratory compaction. So, inertia of system. So, vibratory compaction is basically, you can understand that it is basically the mold is kept over a vibrating table, and because of the continued vibration it basically facilitates arrangement of the powder particles in close spacings to each other, and it also ensures connection between the powder particles, which serves as the locations where from the densification gets started at the onset of sintering, and also it can facilitate uniform density distribution in the sintered parts with minimum presence of porosity. So, so that is why vibratory compaction is useful for brittle powders. Otherwise, there is a chance of crack development if pressure is applied instead of vibration. So, in this case vibration is serving as a replacement to the pressure applied pressure that generally applied for other unaxial compaction routes. So, the important variables in vibratory compaction, it is the inertia of the system. So, this is a powder aggregate which is kept over a vibrating table and which is basically undergoing vibration. Okay. So, so the larger the system, more the energy required for packing. Friction force between particles. So, more friction results in the need of more kinetic energy for compaction, and particle size distribution. So, more frequency required if more large particles are present. So, in this case in case of vibration molding of powders. So, vibration cycle is more important, not the period of vibration. So, it is the frequency that is more important and not the vibration time. So, the pressure compaction techniques. So, we have discussed about vibratory compaction, we have discussed about loose powder compaction, where we are basically not applying any pressure, and now we move on to the pressure compaction techniques. So, these techniques involve application of external pressure to compact the loose powder particles. So, pressure applied can be unidirectional, bidirectional or hydrostatic in nature. So methods with applied pressure can be classified as die compaction. This is the most general form that we generally use, that is mostly we use uniaxial die compaction for simpler shapes. And then isostatic pressing, it can be hot isostatic pressing, it can be cold isostatic pressing, depending upon the end properties that are desired in the powder in the part that is to be produced by the powder metallurgical means. And then there is powder rolling, powder forging, and explosive compaction. So these are the pressure assisted compaction techniques. So die compaction, the steps are again pretty similar like we discussed earlier. So the first step is basically blending or mixing. So after we achieve the blending, then we basically charge that blend or the powder mixture within the die cavity, and then we basically achieve the compaction with the onset of applied load by the die punch system, and then removal of the load and ejection of the compact after achieving the desired green density and the shape. And then after that we basically process it by sintering route, which is a thermally activated process, and thereby we can achieve the desired level of density and densification of the powder compact, green compact. So so the effect of powder characteristics for a good compaction, irregular shaped particles are preferred as they give better interlocking and hence high green strength. But please remember, as I discussed before, that although irregular shaped powder particles are giving higher compaction green and also higher green density because of interlocking, but because we are not intending to use the powder aggregate at green state, because in the next stage, that is the sintering stage, this irregular shape poses many challenges, that is pore formation, and also that weakens the structure as a whole. So the apparent density of powders decides the die fill during compaction. So hence powder size, shape and density affect the apparent density. So flow rate affects the die fill time, and once again powder size, shape and density affect the flow rate. So the powder behavior during compaction. So compaction involves flow of powder particles past one another, interacting with each other and with die punch. Number 2 is deformation of particles. So in the case of homogeneous compaction, two stages are observed. So first stage, rapid densification occurs when pressure is applied due to particle movement and rearrangement, resulting in improved packing. So that is the first stage, and in the second stage, increase in applied pressure leads to elastic and plastic deformation, resulting in locking and cold welding of the particles. So in the second stage, large increments in pressures are seen to affect a small increase in density. So in the that is not the intended goal. Also in the second stage of compaction, the goal is to achieve this cold welding between the interparticle connection points. So so the first stage is basically to bring the powder particles in vicinity to each other and to arrange them in a particular mold cavity, and the second stage is about cold welding between the powder aggregates. Okay. So these are the places for cold welding that we generally achieve for the second stage of the compaction, and so there, that is why it is deals with a very less increase in density value. So the green compact produced can be considered as a two phase aggregate consisting of the solid powders and the porosity, each having their own shape and size. So compaction can be done at low at high temperature. So the room temperature compaction employs pressure in the range of 100 to 700 MPa and produce density in the range of 60 to 90% of the theoretical density of the material under consideration, and at higher temperatures pressure are kept low within the limit, because in that higher temperature, because it is already a thermally activated process. So hence for achieving density higher pressure requirement is not there in that case, and moreover in case of higher temperature processes, higher pressure can also lead to damage and failure, crack initiation at the locations where the punches are interacting with the die, And so, in single die compaction, powder close to the punch and die walls experience much better force than in the center, which results in a higher grain density across the sample length. Longer the sample, more the density difference. So, this non-uniformity can result in non-uniformity properties in sintered part. So, this is the case that we have discussed already, like in case of a cylindrical part, like I have told that if you are dealing with a single die compaction, then of course, there can be a density gradient, and that density gradient can impact the location which is adjacent to the adjacent to the punch, bearing higher grain density and simultaneously higher sintered density, and which can cause a non-uniform properties at the sintered state, and also it can it can also serve as the inhomogeneity in anisotropic behavior of the sintered part. Okay. So, so this is a typical example. So, this is the density variation, and hence final property variation can be greatly reduced by having a double ended die compaction. So, in this case powder experiences more uniform pressure from both top and bottom. So, single ended die compaction. So, you can see this is the example. So, you can see immediate beneath the punch, you can see there is high at the corners. So, like this you are getting. So, you tally from here, and then at the because of the lesser pressure transfer towards the bottom, the density is much lesser in the bottom part of the powder aggregate, which is getting compacted in uniaxial compaction by a single ended compaction. But whereas in case of a double ended compaction, where we are compacting from both top and bottom, you can see that at the top, so there is a density gradient that we are getting, and also at the bottom there will be higher density, and then at the corners there will be low density. That is what is observed over here, and that can cause post sintering a barreling effect to the components, which is again not desirable. So, hence the die punch system need to be designed in such a way that they are capable of transferring the pressure uniformly within the powder aggregate, so that we can achieve green compacts with reasonably uniform density, and which can cause achieving which can facilitate achieving uniform density in the sintered part as well. So, with this we are done with this class, and in the next class we will continue with the several other powder processing techniques. Thank you.